So in this video, we're going to look at an example of solving a method of reduction of order problem. Here is our differential equation, and we have one solution. Now, method of reduction of order is a method of solving for the homogeneous solution to a function based on having one of the solutions to the equation. And the idea is that maybe you've guessed some common things that you think are going to work, and you've stumbled across a solution that works. But because in this case this is a second order problem, you need two solutions. How do you find the second solution without continuing to just guess? And so that's what this method is to solve for. Now we can use this method to prove that our tricks for finding a second solution for repeated root problems also works. But we can also use it if we've stumbled upon one answer for things that don't satisfy our constant coefficient or Cauchy-Euler problems. And so the trick for reduction of order is that we're going to guess a solution for y2, which is based on the information we have about our first solution. So we're going to take a function and we're going to multiply it by our first solution. So v times y1. Now v is itself a function of x. And so when we plug this into the differential equation, we have to kind of keep that in mind. So in order to plug this in, we're going to have to take some derivatives. So recall that since v is a function of x and e to the x is a function of x, y prime will be taken from the product rule. So the derivative of the first one is v prime times the second one unchanged, plus the first one unchanged times the derivative of the second one, which here e to the x also doesn't change. And then likewise, we repeat the derivative. We take the second derivative because we have to plug it in to a second order problem. And so if we take the derivative of this, we get another product rule, so v double prime e to the x. And then we take the derivative, the second half of that product rule, we get v prime e to the x. But when we take the derivative of the second term, we also get a v prime e to the x, so 2v prime e to the x. And then the second half of that product rule, v e to the x, because e to the x is the derivative of itself. And so now we plug these things into our differential equation. So this is our second derivative, and we multiply it by x, just as it was here. And then we have our just y prime is just subtracting that, and then 1 minus x times the original y. Now, what should happen when we do this simplification, if we've done everything correctly, all the v terms will cancel out, and we should only have v double prime and maybe v prime. Sometimes both of them cancel, but usually v prime and v double prime will remain. V itself, without the derivative, must go away, or there's a mistake, because then you haven't reduced the order of the problem. So let's distribute. So I've distributed everything here in x. So x here, and x here, and x here. And then I've distributed my negative sign. And then I've distributed my 1 and my negative x. Now, as I said, all the v's have to cancel out. So vx e to the x, positive vx e to the x, those cancel. Negative v e to the x, positive v e to the x, those cancel. And so what I'm left with is this term right here in double prime, and this one in v prime. So I factored v prime out, 2x e to the x, and negative e to the x. And that's equal to 0. Now, in order to solve this differential equation, we now make a substitution. So we let v prime equal u and v double prime equal u prime. And I'm going to move this expression to the other side of the equation. And what we have is we have a separable equation now. It's a first order problem, and we can use any first order technique that we want. But typically, textbook problems will reduce to a separable differential equation. And so we write u prime as du over u, and du over dx, and the dx comes over here, and we divide by u to get that over here, and we divide by x e to the x in order to get that over here. And if we simplify this expression, we end up with e to the x divided by x e to the x is 1 over x, and 2x e to the x, everything cancels except the 2. And so now what we're going to do is we are going to integrate. We're going to integrate du over u, and we're going to integrate 1 over x minus 2. And so when we do the antiderivative of du over u, we get natural log of u. And when we integrate over here, we get the natural log of x minus 2x. Now, because we're going to multiply this by another function, we don't have to worry about the constant, because the constant is just going to show up in the other part of the problem. It's going to be accounted for, essentially, by the original y1. So you don't have to worry about the plus c here. What we do need to do in order to solve for u so that we can solve for v is we need to do a little bit of algebra. So I'm going to rewrite this 2x as e to the 2x so that I can combine it in here. So let's break that out a little bit. Negative 2x is equal to the natural log of e to the negative 2x, right? Because e and natural log will cancel. And so when I end up with an expression that says ln x plus ln e to the negative 2x, I can combine those logs using a multiplication rule for logs and get x e to the negative 2x. And so that's what this side of the expression turns into. And then I can use that, now that they're both just log something equals log of something, I can cancel my logs. And then since u is v prime up here, then in order to get v, I simply need to integrate u. And in order to integrate u, I need integration by parts. And so you can do integration by parts a number of ways. You can do the tabular method that works really well here, or you can just do it one step at a time. That's fine. What you end up in the end with this expression, or something algebraically equivalent to this expression. And so y2 then, this is my v, and y2 was v times my y1. So I take this v and I multiply it by e to the x. And if I simplify that, I end up with this expression. So the e's reduce a little. And so what I have then is I have my two solutions for my homogeneous equation. C1 e to the x was given to me, and now I have C2 2x plus 1 e to the negative x for my second solution. And assuming that I haven't made any errors along the way, then I should be able to take the derivative of this, plug it into the original problem, and get a 0 coming out of the solution. And if I then have a non-homogeneous function, I can then use these homogeneous functions in order to solve using variation of parameters for the forcing terms, for the particular solution for the forcing function. And I would have to use variation of parameters because undetermined coefficients only works for constant coefficient problems.